Since we have just learned about the probability density function of a Gaussian distribution, the other type of plot which is very important, as we saw earlier, is the cumulative distribution function, right? We saw how to construct a cumulative distribution function from PDF when we learned about exploratory data analysis, right? So let's look at what the shape of CDF of a Gaussian distribution looks like. The CDF of my Gaussian distribution looks exactly like this, right? So if X is my random variable, we do know that CDFs always range between 0 to 1. The left bottom is always at 0. The right bottom is always at 1. And for any given, let's take our blue curve here. Blue curve corresponds to a mu of blue curve corresponds to a random variable X, which is Gaussian or normal distributed with 0 and 0.2, right? Now for this curve, one of the important things is what is for a CDF, just to quickly recap, given any point here, right? So what does CDF height represent? It represents the probability that my random variable X is less than equal to this value. Let's assume this value is 0.4. Okay, it looks like 0.4, right? This looks like 0.4. This is 1. This must be around 0.4 or 0.5, right? So what it tells, this height tells me, this height, let's assume, okay, it corresponds to 0.8, right? So what it says is the height of my CDF tells me what is the probability that my random variable X takes values which are less than equal to 0.4, and that will be 0.8, right? That's what your CDF informs us about, right? So the CDF of a random Gaussian variable, of a random variable which follows Gaussian distribution looks like this S-shaped curve. This is also very well recognized shape. But here are a couple of interesting things. If the mean of your random variable is 0, this is where the central point, right? Because our distribution is symmetric, which means 50% of the points lie on one side of your mean, 50% of the points lie on the other side of the mean, right? So the value corresponding to half here, will be at 0. Right, for all these three curves, because all of them have a mean of 0. But for a green line which has a mu of -2, your half on the y-axis corresponds to x equals to -2. Right? So so at mu, wherever the mu is, so here the mu is 0 for these three distributions, the corresponding y value in your CDF will be half, because as you would know, as you can see from our probability density function, that it's symmetric, which means half the points lie on one side and half the points lie on the other side, right? Having said that, the other important thing that to notice is if your variance is small, right? The variance of your blue line is smaller than the variance of your red line, which is smaller than the variance of your yellow line. As variance is smaller, your CDF line for Gaussian distribution becomes more and more gets closer and closer to this line, right? So if it goes farther and farther, so if you look at this red line, it's slightly farther away from your x equals to 0, your y-axis line, right? This is your x equals to 0 line, right? It goes farther and farther away as so this has a much higher variance, right? So your CDF actually goes farther and farther away as your variance increases. Okay? That's one of the important lessons of CDF. There is of course a closed form equation. We saw the equation for PDF of Gaussian random variable. There is an equivalent formula for CDF, but just in the interest of time and just not to go into too much mathematical complexity, I'll avoid that. Of course, you can see that here in this nice table here, what the equation for PDF is and what the equation for CDF is. Okay. Having said this, there is the other concept that I wanted to go into, which is extremely important with Gaussian random variables. That is called the 68, 95, 99.7 rule. So you can find this in the standard deviation page of Wikipedia. As I told you multiple times, I will use Wikipedia extensively because there are brilliant explanations on Wikipedia for those of us who can follow Wikipedia. So it's a brilliant place. So let's assume somebody gives me a random variable X, which is distributed with normally or with a Gaussian, follows a Gaussian distribution. Let's assume I'm given a mean mu, and if I'm given a sigma. Let's just say somebody tells me that my mu is 0 and my variance is, let's say, 2. sorry, my variance is 2, right? Which means, sorry, let's say my variance is 4, just to make the math simple, which means my standard deviation is 2, right? Just to make the math simple here, nothing else. Okay, then I can tell you a lot of things about this random variable x using the 68, 95, 99.7 rule. Let's see. So what it says is, so first of all, we do know that your Gaussian random variable is symmetric, which means 50% of your points should lie on one side of the mean and 50% of your points should lie on the other side of the mean. By the way, this is what your mean is. You just mentioned mean equals to 0. Now the next thing is, between your mean and, so here what is our first standard deviation? This is called the first standard deviation, right? My first standard deviation is 2, so 1 into 2 will be 2, right? So for my random variable x, which has a mean of 0 and a variance of 4, between 0 and 2, I can find 34.1% of my points here. Okay, which means if I actually sample data from my from my Gaussian random variable, let's assume this was some petal lengths or things like that. Of course, there are no negative petal lengths. So let's assume x follows a Gaussian distribution with these 0 and 4, and if I sample values from x, which means if I start taking observations from x, right, I can tell you without actually doing the experiment, as long as x follows Gaussian random, x follows normal distribution, I can tell you without even doing the actual experiment of observing samples and calculating how many of them are there, I can tell you that between 0 and 2, or between mean and first standard deviation, here our mean is 0 and our first standard deviation will be 2, right? 34.1% of points are here, which means, in other words, if my x is normally distributed with a mean of 0 and a variance of 4, so sigma equals to 2 and mu equals to 0, then between my minus 1 standard deviation and plus 1 standard deviation, right? My standard deviation here is 2, right? So between minus 2 and 2, I will find 68.2% of the points. Just imagine, if I know, so for example, if I know that heights of humans follow Gaussian distribution, and if I have the mean height, and if I have the variance or the standard deviation of heights, I can tell you that 68% of humans have a height between this number and that number. I can tell you that without actually measuring thousands or even hundreds of thousands of humans. Similarly, I can tell you that between minus 2 standard deviations and plus 2 standard deviations, there are 95% of points. Similarly, between minus 3 standard deviations and plus 3 standard deviations, I can observe 99.7% of points, right? Which means, let's actually put it this way. Let's assume x represents heights of humans. Let's assume this is Gaussian distributed with a mean value of 150 and a sigma value. So this is my mean, and let's assume my sigma value is 25. Suppose somebody gave me this, okay, after doing a lot of experiments. By just seeing this, I can tell you that, okay, let me write it down here just for simplicity. Let me just erase this, sorry. Let me just quickly erase this. So what I can quickly infer from that is that, so 150 minus 25 is 125. 150 plus 25 is 175. So I can quickly tell you that 68%, because this is 34.1 and this is 34.1. I can quickly tell you that 68.2% of humans have a height between 125 and 175. Right? Similarly, I can tell you that 95% of humans will have a height between 100 centimeters. Of course, there could be babies and youngsters here, between 100 centimeters and 200 centimeters. I wonder how many 200 centimeter folks are there around. Probably my numbers are a little crazy. Probably I should have reduced my variance or reduced my mean. Right? This is slightly absurd, but let's assume somebody gave me the actual values. Similarly, I can tell you that 99.7% of humans lie between whatever. Of course, this is going to get more absurd here because I picked up some random example here. So 150 minus 75, which is 75, which seems okay, but 150 plus 75 is 225. I have never seen men who are 225, or even the tallest people who are 225, except probably a few basketballers out there. Okay, I don't know even if they are 225 centimeters. 225 is massive. It's 2.25 meters. Okay, anyway, but you get the gist of my idea, right? This is called the 68, 95, and 99.7 rule of Gaussian distributions. Very, very simple numbers that you can quickly remember. I mean, after seeing this for so many times, I remember it almost by heart. 68, a lot of people remember the 95% value. There's two standard, so one standard deviation is 68, two standard deviation is 95, three standard deviation is 99.7.